So in this video, we're going to try and derive where the logistic regression model came from. We will mostly work out of the notebook for the first half of this video, and so the slides sort of give a summary of what we will do in the notebook. So you can come back to this if you want later, but since we have the notebook available to us, let's just do that. So we're dealing with data from the 2017-2018 NBA season here. We have two rows for every game that was played in the 2017-2018 regular season. So the first row is in the perspective of the Golden State Warriors, and the second is in the perspective of the Houston Rockets. But you can see that since the game ID, which is the primary key here, is the same, it's referring to the same game. And so this is saying the Warriors lost to Houston. This is saying the Houston Rockets beat the Warriors. Now, there's a bunch of data cleaning that we sort of need to perform so that we can get this data frame where we want it for our purposes. And all of that doesn't really have much to do with logistic regression, so I'll skip it in this video, but you should go look at it if you're interested. What I've done here is I've grouped this data frame by game ID, and so now we only have one row for every game. And I have this new column, field goal percentage difference. Now in basketball, the field goal percentage of a team tells you the proportion of shots that they took that they made. And so the belief is that the higher a team's field goal percentage is, the more likely it is that they win a game. What we have here is the difference in field goal percentages between the two teams that played this game. So this is in the perspective of the team whose name appears here. So what this is saying is, for example, the Boston Celtics shot 4.9% worse than the Cleveland Cavaliers, which is who CLE is, did in this game, and they lost. So here 0 corresponds to losses and 1 corresponds to wins. This is saying that the Golden State Warriors shot 5.3% better than the Houston Rockets, and they still lost this game. Again, the sort of code that we use to get to this data frame is in the notebook if you want to look at it, but this is where we will work from. Our goal will be to predict whether or not a team wins a game given their field goal percentage difference. And so when we have two sets of numerical values, one way to visualize them is by looking at a scatter plot. And so let's do that by using Seaborn's joint plot method. And so this is a scatter plot with field goal percentage difference on the x-axis and 1 on the y-axis. You will see 1, WON that is, only has two possible values, 0 and 1. The points up here correspond to observations where a team won their game, and the points down here correspond to observations when a team lost their game. You can see that as the field goal percentage difference increases, you're more and more likely to win your game, right? So of teams that shot 20% better than their opponent, they all won their sort of matchup. And of teams that shot sort of worse than 15% worse than their opponent, they sort of all lost their matchup. So our end goal will be to predict, given a team's field goal percentage difference, whether or not they're going to win that game. But a reasonable intermediate step might be to model the probability of winning given a field goal percentage difference. What we can then do is say if a team has a high predicted probability of winning a game, we classify them as having won, and if they have a low predicted probability of having won that game, we classify them as having lost. So, in such a probability model, we might say the chances of winning if your field goal percentage difference is very high is very close to 1. If your field goal percentage difference is very low, we might say that chance is, pretty low or close to 0. And if your field goal percentage difference is close to 0, meaning both teams shot roughly the same, we might say that sort of the probability of winning is roughly 50%, because it could go either way. And so we want to model the probability of winning given your field goal percentage difference. We already have a model that we know and love, the ordinary least squares regression line. So why don't we try using that on this data and try to interpret the outputs as probabilities? And we can do that, again, using Seaborn's built-in joint plot method. And to come up with this line, I set kind equal to reg, which means that this is a regression plot. I could have used Seaborn's LM plot instead, but I decided to use this for consistency. And you'll also note that I set y jitter to 0.1. So you'll note that the y values on this plot are more spread out vertically than they are in the original plot. And that's just so that we can see sort of a better picture of where the y values are. But this green line is fit according to the original data. This is just this jittering is just for visualization purposes. And so now we have the simple linear regression line that passes through our data, right? This model has a mean squared error, right? Because for each observation, I can sort of calculate how wrong my prediction was. And this one in particular, the one we have in green, is the simple linear regression line that minimizes mean squared error for this particular set of values. How does it do when it comes to modeling our values? Well, there are a few issues. One is that we are trying to model probabilities, but the output of this line is not restricted to be between 0 and 1, and we know probabilities must be some number between 0 and 1, right? What does it mean if the output of this line is, minus 0.75? How do we interpret that as a probability? We can't really. But, you may say, well, can't I just say anything that is greater than 1 or less than 0 is 0 or 1 respectively? Well, you could, but this is not the only issue with this linear regression line on this set of data. It is also very susceptible to outliers. And to show you why, let's look at an example. What I'm doing here is, making a copy of my game's data frame, and I'm adding a outlier row to the very bottom. So I'm setting the game ID and the team name to be whatever, because those aren't important here. I'm going to say that this team won their game, and so that's why this value is a 1. And I'm going to say their field goal percentage difference is 120. Now, recall, we're calling the column field goal percentage difference, but this is really measured in proportions, right? 0.1 means the team shot 10% better than their opponent. And so 120 here really means 120 100% better, so 12,000% better, which, of course, that's not a realistic value, but this is sort of here just for the purposes of showing you what an outlier will do to our model. And you can see that things don't turn out so well. You can see that this simple linear regression line is dragged way over to the right just due to the existence of this one outlier at x is equal to 120. And the reason it's above 1 is because of the y jitter again. You might note that in the original line we drew, any observation whose field goal percentage difference was above around 12%, we predicted the probability of winning to be 1 or greater. But over here, this green line doesn't cross the y is equal to 1 sort of level until x is equal to 80, which is way outside of the range of these values, which again are 0.1, 0.2, so on and so forth. So the simple linear regression line is not bounded between 0 and 1. It's very susceptible to outliers, and there are also a multitude of other reasons why this is just not a good idea for trying to model probabilities. So we need a better model. You may remember from the simple linear regression lecture, the way we came up with the simple linear regression model was by splitting our x-axis up into bins, computing the average y value for every x value that was in that bin, and looking at that graph of averages. And we can do the exact same thing here too. Here I'm using pd.cut to take my x values, which are the field goal percentage difference column from games, and splitting them up into 20 different bins. And so when I look at bins, it tells me for each row of games what bin that observation belonged to, according to whatever its field goal percentage difference was. Don't worry too much if you don't understand that specific line of code. What I'm then going to do is, instead of telling me, what the left and right endpoints of each bin is, I'm going to take the average of the left and right endpoints and say that each game belongs to this position on the x-axis. And so now, instead of having 20 bins, we just have 20 spots on the x-axis. And what I'm going to do is compute the average y value for each of these 20 bins. And so you can see, for instance, game ID ending in 2 and game ID ending in 5 both fall in the same bin, and so they would sort of be computed within the same average. So let's go ahead and do that. So I have my games again, and I have the bins along with them. What I'm going to do now is group by bin, then take a look at the one column for each bin and take the average of all of these ones and zeros. The average or mean of all of these ones and zeros will be telling me the proportion of times a team won when their field goal percentage was, in this bin. So when I do that, I get the win rates by bin, which looks like this. The indexes are the 20 bins, and the values are the proportion of observations that fell into this bin that were a 1. So it's the percentage of times a team won when their field goal percentage difference was in this bin. And you can see, as we expected, as the sort of value on the x-axis increases, the number of times you win also increases. What I'm going to now do is plot this relationship, and what we are about to see forms the basis for all of logistic regression. So brace yourselves, this is going to be big. Whoa. This is the graph of averages similar to the one that we computed when coming up with the simple linear regression model. So what this is saying is that on average, if a team's field goal percentage difference was, 0.05, so you shot 5% better than the opponent team, you won, or teams in our data set won, roughly, 75 or so percent of the time. If a team's field goal percentage difference was minus 10%, so you shot 10% worse than your opponent, such teams only won around 5% of the time. And so this graph is the one that we are going to try and model. Before we do that, let's overlay this red graph of averages on our linear regression line. And you can see that this red graph of averages does a much better job of modeling our data than this green line does. It doesn't have those problems of sort of being outside of the range 0 to 1. It's restricted to be between 0 and 1 because it's a proportion, right? The way we created it, by definition, it can't be outside of the range 0 to 1. And so what we now want to do is talk a little bit more about what this graph of averages exactly is. You can think of it as being the empirical probability of a team winning given their field goal percentage difference. And this is precisely what logistic regression models. Logistic regression models the probability of belonging to class 1, right? So where our y value is 1, given some x value. Now, the more general logistic regression model can handle any number of features, and what we're looking at here is just a single x feature, but you get the idea. Now, I'm going to do something that seems kind of magical. I'm going to define this sigma function, which might seem like it's coming out of nowhere. And I'm going to plot, along with this graph of averages, the graph x and sigma of 30x. Okay, bear with me for a second. You can see that in black, I have, x and sigma of 30x, and in red, I have the same graph of averages. And my black curve matches this red graph of averages almost exactly. So the question is now, what is this sigma function, and why does it match our values so well? And so we're getting there, but in the meantime, I want you to think about something. Here, again, I'm visualizing the win rates by bin. What I want you to think about are the answers to these 3 questions. What is the probability that y is equal to 1 if x is 0.0283? What is the probability that y is equal to 0 given x is equal to 0.0283? And what is the ratio of these 2 probabilities? Pause the video, think about that for a second. Did you think about it? Hopefully, I have no way of checking because, we're not in person. We can see that when field goal percentage difference, or x in this case, was 0.0283, the probability of winning was 0.705 or so. So that means the answer to the first question is 0.705. The probability that y is 1 given x is that. Since we are dealing with binary classification, meaning that you either win or lose, y is either 1 or 0, The probability that y is 0 given this x value is 1 minus whatever this is, so roughly 30%. So the probability that y is 1 given x is roughly 70% here, 30 for y is 0. The ratio between these things then is roughly 70 over 30, which is 2.33 or so. How we can interpret that is that for every 2.33 games a team won, they lost one game. That is, if their field goal percentage difference is 0.0283. This ratio of probabilities is called the odds of an event. So if some event happens with probability p, then the odds of that event happening is defined as being p divided by 1 minus p. And so what I'm going to do is look at the odds by bin for each of these sort of 20 positions on the x-axis. So I'm going to take the win rate by bin and divide that by 1 minus win rate by bin, because we're interpreting these values as our probabilities. And when I do that, it seems like these keep on increasing, and it goes from 3 to 9 to 64 to a bunch of things that are infinite. The reason these are infinite is because their p's, their probabilities are 1, and that means the denominator is 0, and of course you can't do that. But anyways, if we look at this plot, it looks exponential of sorts. And how do we take exponential data and convert it to being linear? Well, we take the log of it. And so now you may see where we're going. But if I take the log of the odds by bin, I get a graph that looks roughly linear. Is it perfectly linear? No, of course not, because no model is exactly right. But this relationship, the log of the odds of belonging to class 1, or the log of the odds of winning, does look roughly linear. And that assumption is what the logistic regression model is based on. So in the next video, we will flesh that out a little more.